coffee was strong enough. I'm going to be talking about massive galaxies, and largely based on work from the Slug survey, which you've also heard from Duncan Forbes about earlier today. There's a lot of collaborators who made this possible. I've bold-faced the ones here, except I left off Usola Labe, who you also heard from, talking about galaxies at the other extreme of the scale, the ultra-diffuse galaxies. So I'm kind of a little bit confused about those at the moment, so I'm switching back to high-mass galaxies and see if we can understand those. So I want to start with a big picture question I don't feel is adequately answered yet. Something you could point to a kindergartner and show pictures of these different types of galaxies, and they might ask why are they like that. I'm not sure we know the answer. So the very basic Hubble sequence, you have elliptical galaxies, spiral galaxies, and these things in the middle that are like the middle child that tend to get overlooked, lenticular galaxies. People don't tend to talk about them as much in their formation models, but I happen to think they may be actually a big clue about how the other types of galaxies form. So how are these galaxies formed? Well, sort of a very classic view of these for lenticulars say, well, they are some classic work showing that there's increased incidence in galaxy clusters. They fits with them being faded spirals. Okay, end of story. And with elliptical galaxies, that they work out nicely at a first glance that they could be formed by major mergers. A lot of beautiful work showing this, and for sure that happens to some extent. As we've heard earlier today, though, there's a lot of other reasons to suspect that's not necessarily the dominant pathway for forming those galaxies. So one more recent model for forming massive galaxies, massive ellipticals, is called the two-phase model, which you've all heard of at some level. Oser and Nab popularized this, and this idea the two phases would be an initial dissipative phase, it's sort of a hand-wavy, not sure what happened there, followed by minor mergers, which gradually built up the extended outer envelope of these giant galaxies. And here's a little simulated picture showing from the illustrious simulation of the in situ central component, first phase, and the outer accreted phase. Now, sort of where the state of the art is with statistics for how you might expect these phases to occur in cosmological simulations. This is illustrious Chi and G from Annalisa Pilipich's work. This is the prediction of in situ mass fraction as a function of halo mass. You see at the lower masses, Milky Ways, it's mostly in situ stars, and in the high mass clusters and high mass groups, they're largely accreted, they're merger dominated. And then there's this transition that happens at about a few times 10 to the 10 in stellar mass and a few Milky Way masses in halo mass. So basically a few Milky Way masses, you start transitioning to this accretion-dominated regime, which is also where giant ellipticals start kicking in. You get group mass galaxies, or halos. Where the transition radius is on this, I'm not sure there's a clear prediction yet. Maybe depending on the halo mass, these ones here, the lower mass galaxies, the transition occurs farther out, a few effective radii. As you get to the most massive ones, basically the entire galaxy is all mixed in by major mergers. And what kind of galaxies are being accreted? Again, it depends on the host mass. The low mass galaxies, you've got sort of fairly massive dwarfs. The higher mass galaxies, you're getting Milky Way mass galaxies that are falling in. This, again, these are from simulation predictions. Well, okay, these are some predictions that are very useful to have. So how can we actually go out and test this scenario and the specific predictions? What observable signatures are there? That's one of the things that Slugs is designed to do. But before I get there, I want to just show a little bit more on I'm going to talk mostly about kinematics, but there's also some work we're doing on stellar populations. This is work that was led by Peter van Dokkum and Charlie Conroy. We used the Keck LRES spectrograph to get long slit spectroscopy out to about effective radius and a handful of elliptical galaxies, S0 galaxies, and look at the wing forward band, or model the full spectrum, but particularly using this wing forward band, which is a diagnostic of the IMF. So you heard a little bit already about the IMF variations. This is one of the key clues for why we think they're IMF variations. Here's the bottom line. If you stack all these galaxies, this is this mass to light ratio excess from dwarf stars, from low mass stars, and with effective radius, and there's a transition at a few tenths of effective radius, inside of which there's this super saltpeter IMF, outside of which it's just normal Milky Way IMF. This has been bolstered by other types of work, dynamics, gravitational lensing, et cetera. But what are the implications? And one implication is that if this is the first phase of massive galaxy formation, something very different happened at the star formation feedback episodes there that created a different stellar population. And as far as I know, no one's quite grappled with what that means for the star formation at those epochs. And another implication is, Duncan alluded to this in Asher's work, is when you do dynamical modeling of galaxies to try to decompose the stars and the dark matter, get their halo profiles, you have to take this sort of effect into account in getting a good handle on whether you've got a cusp or core, for example, and that's what Asher has pioneered that work to disentangle that. So I'm not going to talk any more about that. I'm going to move on to kinematics, and starting with this wonderful Atlas 3D survey using the Sauron spectrograph. It's sampled hundreds of galaxies in the nearby universe out to about 1 effective radius with 2D kinematics, blazed the path for other surveys like Manga, Sami, Khalifa. So here are 2 examples. So using this thing, I'm going to come back to this. It's the Lambda spin parameter. It's basically a V over sigma type metric of the rotation dominance. And here's an example of, you can see by this color coding is the rotation, a very fast rotating galaxy, relatively speaking. This one, it's more chaotic looking, also called a fast and a slow rotator. So this is one of the classic diagrams that the Sauron folks have pioneered of the lambda versus ellipticity and seeing where the galaxies lie in this diagram, now adding some SAMI data. Most of the galaxies are in this, what they call a fast rotating region, high rotation and more flattened isophotes. And then there's these slow rotators here, also called the regular and the non-regular rotators. Is this a continuum? They've done a lot of detailed work to look at this and say that no, it's not. There's a dichotomy here. This is a histogram of basically kind of a V over sigma type metric. And there's this tail of this low rotation here and this peak of fast rotation where there's 2 different types of elliptical, or early type galaxies, I should say. It's not ellipticals. It's no longer the dichotomy between ellipticals and lenticulars, but here's some of the ellipticals here, the small histogram, and these are lenticulars. So there's a fast rotating population of ellipticals, which on these scales look indistinguishable from S0s. And then there's these slow rotator ellipticals, the more massive ones, that seem to be something different. So it's a new type of dichotomy seen on these scales. And I'm going to come back to this, that a lot of conclusions may be scale dependent depending on where you look in the galaxy. Okay. So where's sort of like after the years of the Atlas 3D survey, what have they come to and what do they conclude about early type galaxy formation? Here's a plot of a size versus mass of galaxies of all types, from dwarfs to the giants, and they're showing this continuum from late type spirals to the earliest type ellipticals, that as you go down, as you increase in mass, increase in density, a lot of things change smoothly, like gas fraction, mass to light ratio, the IMF, stellar populations, that sort of thing. So they end up, from lots of different lines of evidence, they end up coming up with this scenario where you've got 2 modes of galaxy growth for massive galaxies. I say that's non-dwarf galaxies, basically, where you've got most of them are growing through gas accretion until they hit this red sequence, and then as they get the most massive red sequence galaxies, they're growing by minor mergers, or sorry, dry mergers, not necessarily minor mergers. That's maybe not a big surprise given a lot of other lines of evidence from high redshift, et cetera. Where did the fast and the slow rotators fit in? Here's a picture where the slow rotators are these red things and the fast rotators are the other more flattened things. And it's this picture where the slow rotators are the centers of proto-massive halos, and they start merging with other things that fall in and scramble around the central galaxy. Those become the slow rotators, while the fast rotators were their earlier late-type galaxies. As they fall in, they get more smoothly quenched and don't experience the same type of merging, and they preserve this sort of spiral-type structure. So that is Atlas 3D scenario for early-type galaxy formation. So part of this, what I understand is, and again, most of the galaxies, you hear about fast and the slow rotators, and the slow rotators are exciting in some ways, but most of early-type galaxies are in this fast rotator class. I would say the vast majority, 85, 90%. And one of the questions we ask is, again, is there really a continuum from the spirals to the S0s to ellipticals, structurally, chemically, and everything else? And is it composed of disks and spheroids that have their own distinct properties? If so, does that imply that there is some universal formation mechanisms for disks and bulges, or are there multiple ways to make disks and bulges? And I should point out that this is something that can look at in simulations. Also, some semiotic models have looked at over the years. Starting with disks, disks are relatively easy to reproduce, the scaling relations of disks, the sizes, et cetera. Bulges, there seems to be still more of a struggle. Some of the bulges may be formed by mergers, some by disk instabilities, and this is showing the size versus mass from one semiotic model. These dotted lines are observations, and this curve is the SAM reproducing the disk sizes, while here it's showing it's struggling with the bulge sizes, and mainly because most of their bulges from disk instability, which produce these really tiny bulges that are not what are observed. At least that type of disk instability, so I'll come back to that. So there's work to do in understanding where bulges and disks come from, and I'm going to talk about angular momentum from kinematics as one of the diagnostics for the formation histories. So one way to look at this is to plot the angular momentum versus stellar mass, and this is a classic plot first shown by Mike Fall, and over the years we've refined this. This is our latest version that will be coming out in the archive on a couple days. And this is color-coded by bulge fraction, and there seems to be parallel sequences with bulge fraction of in this J over M space. They're about 2/3 power law slope, and it implies that galaxies are constructed of these bulges and disks which have separate and parallel scale relations in JM. So one of the new things we did was fit this in 3D space. This is J versus M in bulge fraction. We have this model that represents this, and it fits the data nicely. Where does that give you in terms of angular momentum and cosmological framework? If you map it onto the dark matter halos, basically the disks overall are conserving or retaining about 100% of their angular momentum, while the bulges lose an order of magnitude. So that's a key benchmark. The disks, that's been a benchmark for a long time, which simulations have struggled to match and are now doing. The bulges, it's been less clear what benchmark is needed. So we've been refining this, and hopefully people will look at this in more detail. I'm just going to skip over all this and showing, there's a lot of work on overall angular momentum, just sort of some of the newest work using this bias collapse model to try to get the bulges in the disk-dominated galaxies, where there's a correlation between angular momentum retention and star formation efficiency. Also some nice recent work from the Nihao simulations looking at these trends for the bulges and disks separately. So I'm not going to discuss this in detail, but I just hope people will continue looking at this as your simulations get better and better and try to track down the origins of these scaling relations. So I kind of skipped ahead to some results, but without showing where some of the data come from. How do you get out to larger radii? Soren's done this beautiful work with Atlas 3D at the central regions. Go to the outer regions, the slugs survey is still probably the best, doing stellar kinematics out to about 3 effective radii. Planetary nebula spectrograph survey is going out to about 7 effective radii, and slugs with globular clusters out to about 12 effective radii. So that's how we get to these large radii. Here's a map. I think Duncan might have showed some of this earlier in his talk of stellar kinematic fields. These are like Soren fields, but 10 times the area. What do we learn from these? Well, one is this specific angular momentum or spin parameter versus radius. This is the Soren region. Things tend to look kind of homogeneous in here with these rising profiles unless they're slow rotators. As you go farther out, you get more diversity. Some of them keep going up, some of them go down. So it's starting to tell us that these central regions are not quite enough to tell us what's going on. So what do we do this? Duncan did some interesting work to try to piece together all the information we have from the stellar kinematics, and I won't go into the details, but matching these up to a suite of cosmological simulations, state of the art at that time. And this is a lambda versus stellar mass plot, and I can't go into all the symbols, but the bottom line is that the inference was that the highest mass galaxies were dry merger dominated, consistent with the picture I showed earlier. The L-star ordinary galaxies are these ones here, and all these blue symbols are basically galaxies with high in situ fractions and very little impact from major mergers. I think I'll skip over this just to skip, but it's showing that we can look at tracks in angular momentum ellipticity space, and as you go out, then things kind of actually can turn back, and you can start getting downturning spin profiles of these galaxies. So, but I want to push out to larger radii and say that's sort of pushing the stellar kinematics at their current state-of-the-art limit. We're doing more work with KCWI to try to push that out farther and better. But the best right now we can do is using planetary nebula and globular clusters again to create these complete kinematic maps using all the data combined out to large radii. And looking at things, now we can start decomposing the bulges and disks. This is some work that Ariana Cortese did with her student Amelia Zanata on a bunch of S0 galaxies using planetary and globular clusters. And you can get the bulge and disk properties separately now that you've got these wide fields to decouple a lot of the degeneracies. And one of the inferences is that the S0 disks are fairly warm or hot, V over sigma 1 to 4. So this is hotter than the spiral galaxy disks. So they're not simply faded spirals. There's either some sort of pestering that's gone on to heat the disk, or they were born hot. Maybe it's some high redshift turbulent disk formation mechanism, kind of like you heard about with M31. And Duncan already showed this thing. I'm going to skip over that and skip to now a larger sample of this edge-on early type galaxies, and you might see a common rotation pattern where there's a high rotation in the center and low rotation in the outer parts. Okay, so there's this kinematic transition, so this might be the in situ, ex situ transition for these galaxies. And this is a V over sigma profile showing this generic pattern of them decreasing with radius, also having mild kinematic twist. We can compare these to major merger simulations, 3 to 1, 1 to 1. I won't go, and these are cosmological simulations you'll hear about from Avishai and Daniel, I expect later in the week. These are these ART simulations with disk compaction and what I call wild disk mode at high redshifts. Just to summarize how these look, these are the kinematic fields from observations compared to major mergers. They don't resemble them because they put a lot of angular momentum in the outer parts. These cosmological simulations show this two-zone rotation pattern. And as everyone's simulations get higher resolution for these massive galaxies, I'd encourage you to look for this and see how often you find it. And it's something we can compare to the observations. So this is more of the technical details you can ask me about how we get to these interpretations. Again, the idea is you've got this in situ and ex situ modes, and we can try to pin a more specific model for this in situ formation of these turbulent disks at high redshift with bulge formation through compaction and clump migration to the center. So let me just summarize the overall. I've covered a lot of ground, but some of the main points I wanted you to take away are we have these angular momentum versus mass relations over the full Hubble sequence, which we can pin down to separate bulge and disk relations, and that is a key observable for constraining galaxy formation models. And hopefully understand where bulges and spheroids come from. More detailed kinematics are showing this two-zone kinematic pattern in early type galaxies, which suggests two distinct types of assembly mechanisms, which we think may be linked to this what we call wild disk mode of the turbulent disk followed by minor mergers. So thanks for your attention.
Some questions then? Dave.
Mm-hmm. The terminology is a little unclear when you get to these early type galaxies, and when you call it bulge or spheroid or halo. It's not like the Milky Way where there's a really clean separation between, here's the disk and the compact bulge, and then here's the halo. But you're starting to get this mixing of everything, and so on purpose I was a little ambiguous with the terminology. But there's this accretion zone where you do have accreted stars from both a metal-rich and a metal-poor component. We can start picking that apart using globular clusters to look at the different metallicity populations.
Rather than the morphological structure, you like to discuss the origin of that concept.
Yeah, by looking at the kinematics and the metallicities and chemical abundances and ages, yes.
That was a lot to digest.
Mm.
Do you think that you could sort of encapsulate the conclusions in a couple of sentences that we can take away here?
So the conclusions is we're starting to get a global view of early type galaxies, of what their structural components are, the chemical, kinematical components. And the simulation should now be able to start looking at those that have enough resolution, hopefully, including AGN feedback where you believe your massive galaxies. to start seeing if you can understand where those components are coming from, and if they're not showing up the way they're observed in the models, what does that tell you about model adjustments?
Could I just get you to amplify a little bit? Could you tell us maybe, you know, 1-2 punch, think about this model and think about that model?
See if you can tell the difference between these components formed through mergers and through disk instabilities and the type of disk instability you can get, for example. Violent disk instability in particular.
Okay, one last question. So what's the possibility, so I understand that you take the fact that there's a rotation in the outskirts that we don't have major mergers. So I guess it's your basic question. What's the possibility of having a disk which is being revealed around this? And so I guess you need ages or at least mechanistic gradient or something.
Yeah, that's exactly, I mean, there could be multiple, for sure there are multiple mechanisms for creating spheroids and disks, and you could get rebuilt disks. It's a question of like, what are the most common mechanisms, and when you see two things that might look identical in photometry and kinematics, can you use things like ages and metallicities to tell the difference? And that's the sort of thing that we're trying to work on.
Let's thank Aaron again.